In this video, I'm going to walk through the steps needed to find a derivative algebraically. So we'll be using the new algebraic definition of the derivative. So here's a graph of the function, and we're asked to find the derivative, which is the instantaneous rate of change, or the slope, at x equals 1. So I've plotted a point there, and I can see the function is decreasing. So the function, which is in red, is decreasing at that value. So therefore, I'm expecting the derivative, which is f prime at 1, to be negative, because the derivative is that rate of change. And it's decreasing pretty quickly, so I'm expecting a fairly large value. To get a better sense of things, I'm going to try to draw the tangent line to this graph. So I'll start just up here and then try to bring it down so that I think that it is tangent at that green point. That looks pretty good. So now we'll try to approximate the slope of this. I'll do a slope triangle. This looks like a nice point to choose, and then another one maybe about here. So this is a run of 1 unit. Notice my scale is 2 to 1, so that's 1 unit. And then a drop of about 6.5. So that would be rise over run, so negative 6.5 over 1. So this is what I think the derivative is, about negative 6.5. So now we will look at doing this algebraically. The definition we established in class looks like this. It's a limit of a quotient, and in that quotient we are finding an average rate of change. So it's a change in y values divided by a change in x values. And we want that change in x values to approach 0. This is similar to what we did in class, finding instantaneous rates of change. When we find an average rate of change as a rise over a run on an interval, we go from some x value to a little bit beyond it. For example, from 1 to 1.1, from 1 to 1.01, from 1 to 1.001, and so on, looking for a limit, which is the instantaneous rate of change. So in all of these cases, the amount of change in yellow is decreasing. It's approaching 0. Those are our h values. And back over here in the algebraic definition, we see h is approaching 0. So now let's work with this particular function at x equals 1. I'll substitute 1 in everywhere I see an a, and that will give me that the derivative at 1 is the limit as h approaches 0 of f of 1 plus h minus f of 1. Here in the bottom, notice the a's will cancel, so I'll just be left with h. I will now substitute in my values into the function. 1 plus h becomes the input, so I put it where the input is in the function, and I get a limit expression of negative 3 times 1 plus h all squared minus negative 3 times 1 squared. That's what the function says. The whole thing is divided by h. The next couple of steps are simplifying steps. I'll open up these expressions and combine like terms. So I get 1 plus 2h plus h squared as the square of the binomial, and all over h. Distribute the -3, giving me -3 minus 6h minus 3h squared plus 3, all over h. I notice at this point that the -3 and the 3 will cancel, leaving me with the limit as h approaches 0 of -6h minus 3h squared all over h. I want to know what happens to this expression when h goes to 0. But if I just substitute in 0, it is undefined. This is the whole idea of a limit, though. We don't care that it's undefined at 0. We just want to know what happens near 0. That's the idea of the limit. Algebraically, we might be able to find this if we can rewrite the expression so that h is not there. And I see that h is a common factor in the top. So if I factor that out, I have this expression allowing me to cancel the h's and giving me an expression which is defined at 0. Sorry, do that again. That'll be -6 minus 3h. So now what happens when h goes to 0? Well, if h goes to 0, so does 3h. And so -6 minus 3h just becomes -6, which is my limit. Now let's look back and see how this compares to our prediction from the graph. It looks good. Our prediction was around -6.5. We got -6 algebraically. Those are consistent results. We would never expect to get the kind of precision from a graph, especially a hand-drawn approximation of the slope compared to the algebraic, but we should expect to be able to see that our results make sense, and these do. So let's now confirm this algebraically.